It's my pleasure to introduce James Forshaw. James is a principal consultant for context information security in the UK. And today he's going to be talking about the binary protocol analysis using his CANAPE tool, exploiting binary protocols. Take it away.
Yep. Good evening. Nice to see so many people actually coming at this late hour. I would probably be rather in the pub or even watching Hacker Jeopardy, but there we go. So what am I actually here to talk about? The main thing is I'm going to talk about my networking tool I wrote called Canapé. And to demonstrate its flexibility, I'm going to try and take apart, hopefully live on stage, a VMware ESXi networking management protocol. So I'm going to be doing things like man-in-the-middling, traffic parsing, all that sort of stuff, and hopefully a bit of fuzzing, maybe a bit of crashing of some processes. Hopefully not Canapé, but we'll see. So Canapé has been out for about 12 months now. It is a free tool, sort of as in the beer sense. Unfortunately, it's not. The source isn't open, but it is written in .NET, and I've not obfuscated it, so it's fairly easy to find out how it works. And it's designed for network protocol analysis and network protocol manipulation. So there's plenty of existing tools. So if you're doing a web application test, for example, you're probably quite confident using things like Burp Suite or CAT, which is the context equivalent of that. But they really only are specialized for HTTP traffic. Now, there's also other tools such as Echo Mirage, which is sort of more for binary protocol analysis, but it's quite limited in what you can actually do with it. There's a bit of scripting, a bit of functionality, but it's a bit simplistic. Obviously, there's plenty of libraries. There's things like the fuzzing libraries like Sully, written in Python, or there's various Ruby applications which you can use, which do sort of similar things. And obviously, there's Wireshark, which does sort of man at the side or sniffing protocol analysis, but doesn't really allow you to manipulate the traffic itself. So the reason I wrote Canapé was I kept going on jobs on site somewhere, finding that I had some sort of bespoke binary protocol, fat client, client-to-server type protocol. And every single time I went there, I'd have to write some sort of application, because even if you're using a library to do your sort of protocol analysis, you generally still have to write the socket server, or if you do, you may have particular criteria you need to meet. So you would usually use perhaps Python or Ruby, if you're really brave, a bit of C, C++. And that would be it. And it just annoyed me that every time I had to do this, I had to go back from scratch, rewrite everything, if I wanted that sort of flexible man-in-the-middle proxy, which allowed me to actually do my job quickly. So the way in which Canapé is sort of different, or at least reasonably different from most of the tools I've already demonstrated, or already pointed out, is that it is completely GUI-driven. So while it can write code, and there's a number of supported languages, it is a Windows-only application, so it is written in .NET. But the advantage of .NET is it's quite easy to write dynamic code for it. So Canapé supports C#, has inbuilt IAM Python, IAM Ruby. If you're really crazy, you can do Visual Basic or JavaScript.NET. And if you're of the functional bent, there's even F# if you want that. And basically, you can almost plug in any .NET language you like. And it also comes with a sort of library of primitives which you can use in your protocol analysis and protocol manipulation. It doesn't come with a vast swathe of protocol parsers, say, like what Wireshark would come with, because it was really designed for those cases where you're finding a protocol which is completely bespoke. There's no documentation for it. There's no Wireshark dissector. And you want to get it sort of done as quickly as possible. So Canapé works more along the lines of the HTTP application proxies, like Burp and CAT, in that it provides a TCP level socket, TCP level proxy, so in this case SOCKS. It can also do HTTP, and there's things like SSL man in the middling, which if you could come across a protocol which is using SSL, it's kind of like a very quick win to just add that in, and you're hopefully then decrypting traffic. And also does UDP, broadcast traffic. But it can also, not just proxy stuff, it can also act as a client and also as a server, so you can write exploit clients, exploit servers, do fuzzing, that sort of stuff. Now we actually have to go on to what the ESXi protocol is, or what I'm going to now try and dissect. And VMware ESXi is a sort of managed platform, managed VM platform produced by VMware. You can stick it on bare metal, just run it as is, and you have to actually talk to it some way. So what there is, it exports various TCP sockets, and you can use that to do things like remote desktop or uploading files to the ESXi server. But this requires a bespoke client, which looks a bit like that. And with a bespoke client, invariably, they decide to come with some sort of bespoke protocol as well. And yeah, you've got multiple different protocols it's using. As I say, you can do sort of file copies and these things. And the sort of bespoke side of things, while it uses a bit of HTTPS to do some sort of control information and logging and that sort of stuff, the actual sort of remote desktop protocols, the file copy protocols, are all this bespoke binary protocol. But it's also slightly complicated. It's not just a simple protocol. So it's not just a simple wrapped protocol in SSL, goes down one channel. Unfortunately, they keep upgrading and downgrading to and from SSL during the operation of the protocol. So you can't just sort of use S-tunnel or something like that, or OpenSSL directly just to talk to the server. You actually have to have a bit of logic in there to actually manipulate the protocol. So, as I say, it's demo-laden. So first thing I'm going to do is actually man in the middle of the traffic. So if I bring up Canopy, if you are experienced of sort of general development environments, it is basically sort of an IDE for bespoke binary protocol analysis. It can do other protocols, it can do text protocols, but it is sort of focused around binary protocols. But I've said it only actually provides a proxy. It doesn't do process injection or anything like that. So you still need to actually get the traffic in there. So in this case, it depends on the application itself. If the application provides proxy settings, you can use that to push the traffic through. In this case, VMware doesn't provide any proxy settings, or at least that I've been able to ascertain. So instead, I'm just using a nice tool, Proxifier, which will basically proxy an arbitrary application and turn it into a SOCKSified application. And there's various other ways of doing this, depending on what you're actually trying to achieve. So it's simple enough. It comes with, as I say, servers, fixed proxy. So fixed proxies just listens on a local port and port forwards it to somewhere else. But in this case, we'll create a SOCKS proxy. And there's various tabs in here. It's a bit of a complicated interface, but it's quite a complicated application to actually use. So the two main things on here are the settings, so we can set what we're listening on, and the packet log. So this is going to be where we see packets coming through. So we click Start, and if we run up VMware, cross your fingers it actually works. Okay? That looks possible. Obviously, I declined to pay for it just now. I'm evaluating its security, you see. But now we've got packets in there. So if we actually expand this out slightly, if we look at the network, if we can actually see that. Port 443. So port 443, HTTPS. Seems a reasonable bet. If we try and do something else, so for example, we'll go and try and upload a file. Obviously, I've already copied my passwords on there, but I'll just do it again. It should go. So that's worked. So if we now look, and hopefully, somewhere down the bottom somewhere, we now have port 902. So this is now our bespoke binary protocol. And we can actually look at this. And it will provide you with just a simple sort of editor viewer interface, which we can sort of go through. And as you can see, if you know what SSL looks like from a network layer level, this is basically it. That's the certificate coming down for the SSL connection. And we can't see a lot. Of course, in this case, being that it's a secure file transfer protocol, they transfer my passwords in plain text. But close enough. So that is man in the middling. Now, perhaps we want to actually look a bit at how what is being transported in the HTTPS layer. For that, we're going to have to actually break into the SSL. So the proxies themselves come with, they are effectively agnostic. They're designed not to care what protocol you're pushing through it. So unlike, say, a HTTP application proxy, it doesn't automatically assume that port 443 is SSL. Because what if it's, for example, some malware which is trying to use 443 as just to evade a firewall? So you actually have to tell Canopy, you know, I know this is SSL, let's take it apart. So in this case, we specify port 443, and under SSL, we turn on SSL. And that should be it, although if I use the auto-generation function, which is usually the best way to do it, VMware has there's some weirdness with its SSL certificate, so it doesn't work so well. So I'm going to cheat at this point. Because I know that it's my server, I can pull the SSL certificate and private key off the server itself and use that, hopefully. OK. So that's the import of the SSL certificate. And now if we run this again, it'd help if I started the SOX proxy. That's the first failure today. OK. And we should hopefully see that our SSL is now taken off. So we've got our plain text HTTP, and we can start manipulating that. So but the HTTPS isn't that interesting. It is a bit, but really we want to get into the binary protocol. This is what Canopy is designed for. But as I was saying before, it's not the sort of simplest of protocols. So at the very least, there's usually 3 states. So the first state is a banner is sent from the server and says, hi, I'm a VMware ESXi server. It will then do authentication under SSL, and then will then transition usually into the final protocol. So this could be sort of the VNC remote desktop protocol, or the NFC, which is the file transfer, which I already demonstrated. And that doesn't use SSL, or at least by default. So now I've got to handle the state transition. And one of the things I've tried to design it for is, where possible, to minimize the amount of coding you would ever have to do on at least a simple protocol. Obviously, if you're going into completely bespoke encryption or custom checksums, you may actually need to start implementing sort of your own code. But Canopy does support that. So let's go for, so we know 902 is our protocol, so we want to use that. And the way in which we actually implement the functionality in between the sort of connection to the proxy and the client at the other side is using what I've termed as net graphs. So this is sort of, looks like that. So it's a directed graph which indicates, or can indicate, both data flow and state. So it's sort of a bit of a mix. But effectively in here, server. This is always massively confusing, but server actually goes to the vSphere client. And client, which is the sort of client TCP connection going out, is actually to ESXi. So that at least makes it slightly more obvious, maybe. Just rename that just to give us a better idea. And we now need to implement some state. So each of these nodes is sort of an independent unit. And these logging parts of the graph are actually where, surprisingly, the logging happens. If you have no logging elements in your graph, they will never appear in that packet log, which I showed before. So again, Canopy doesn't assume that it knows better than you whether you want to log a packet or not. So there's various built-in nodes, but I'm going to choose the switch node, which, oops, if I use the right one. And this is, as its sort of shape would suggest, some sort of decision element. In fact, it's sort of akin to a switch statement in C or Java or C#. And this is sort of exec state. And the way in which this works is it looks at a particular property of the connection. So you can, for example, store the current state as a text string. So, for example, you could have initial state, authentication state, VNC state, and basically just looks at that, and based on this path, this selection path, which is one of the properties you can specify on that node, it basically allows you to, say, do a decision based on that state. And hopefully, let's check I haven't done anything stupid. So we just need to actually then act on that, we can annotate the edges of the graph. So what we actually need to do is implement the SSL. As I see, it can get quite complicated quite quickly. But we can basically draw in a couple of lines. This is done using either the middle mouse button or holding left control and the left mouse button. And that then has connected that part of the graph up. So this is our auth layer. So we also now need to put it on the opposite side, because we need to do the reverse leg. Because basically the two legs are completely independent of each other, and you need to basically put it back the way it came. So, all very pretty. If we just annotate our lines, and in theory, this might start working in a second. So I just need to specify that we want SSL as well. Because basically the way it works is, as it goes through, it will automatically initiate the SSL connection and actually do the job. And this uses exactly the same certificate everywhere. And then there's one final bit which I need to add, and that is actually to set the state. At that particular point, nothing is ever going to set the state, so it would be kind of uninteresting. But we actually need to, if I just capture quickly. So we need some indication. So that banner which came through, what we want to do is use that banner as the mechanism to determine when we change state. So if I just quickly grab the banner from here. So I can find it. Okay. So I'll just take that and I can stick it. If I add my, so this is the library selection. So basically these are all the nodes, extra nodes which are externally implemented. So the core of Canopy just contains some sort of basic decision elements and logging and that sort of stuff. But anything a bit more complicated can be exported as these library nodes, which are implemented in native, well, C# or could be native code. But I haven't even got into scripting yet, so I just need to add something which will set my state for me. And we want to set auth. And every node contains a list of filters. So this is a list of things which allow you to specify what packets you want to handle. So in this case, we know that we want to match on some binary string at the beginning. So now if a packet comes through with that banner, it will go, right, okay, I need to perform my action. The action of that node is to set the current state to the authentication state, and everything should hopefully work. So, okay, stop that. So in order to do this, we just need to now say, don't use the default graph, use actually a completely different one in part of our filters. So HTTP is still going to go over the same networking protocol. So if we upload a file, that's not a good start. I knew my demo is going to go wrong. Oops. Oh, I know why. That sort of bidirectional thing actually needs to specify some sort of graph, which actually says what it's actually going to contain, because it allows you to manage the complexity of, if I had to put that all into one big graph, you'd just be here all day. So okay, and I expect it to fail, because basically it's not now transitioning back into the third state. But this should at least demonstrate that we've now got decrypted traffic, hopefully. Yeah, so we had now, that was our banner, but now we've got other protocol. So this is what was wrapped in the SSL before, and so on and so forth. Then it does a connect, and then you can manipulate it, and you can now get into the NFC protocol. So yeah, the authentication protocol has various different ways in which it can be used. So for example, there's a sort of user, just a simple plain text user password authentication, but obviously it's SSL, so it shouldn't matter. There's sort of session authentication, various different things. So I want to quickly do a very simple fuzzing exercise. Perhaps I want to try and brute force the username and password. How difficult would that be to do in Canopy? So I've actually got one prearranged, hopefully. So as I say, it provides client functionality as well as server and proxying. So in this case, I've got two very simple packets I've captured. So we're trying to log in as root, and we're trying to log in with a password of XXXX, which isn't probably going to work, because that isn't my password. But now we've sort of got into the protocol, we can start doing a bit of fuzzing. So this is, again, a built-in node. This is to fuzz parts of the packet using just text strings. And I have, in my list, 3 passwords. You can probably guess which is going to be the password which will work. So if I now connect it all up. So again, we're using the same sort of graphs which we're already using, so you can take them from a proxy and implement it in your client. So, for example, that looks pretty much exactly the same, perhaps slightly different naming. And if we hit start, you should see, obviously, if I implement it properly. So we start it, so we get login incorrect, password required, login incorrect, because we haven't actually enabled the parser at that point. So at the moment, that is just sending XXX and not doing an awful lot. But if we actually change the way in which it's working, so SSL auth graph, hopefully, unless I've screwed something up. Again, demos never work when you want them to. Sorry. That's because it maintains the states as we go along. So, okay, so now you can see it's sending different things each time. So it's sending password, sending hello, and finally it says password with 5s, and we get user root logged in. So now we'll go a bit into the remote desktop. So this just shows off, again, sort of what you can do without actually writing any code. And the remote desktop protocol is based on VNC, which is fairly well known, but just to spite everyone, VMware adds some extra specific extensions. So even though VNC supports key presses, mouse movements, all that sort of stuff, VMware clearly felt that wasn't suitable. So they implemented their own. But it's fairly obvious. That's a key press. You get the scan code coming through. You get the down, and then you get the up. And you've got mouse movement. So again, fairly simple. So I'm going to try and implement a parser for that, and then I'm going to do some traffic injection just to show that once you've got that connection up and running, you should be able to then actually use the GUI to throw more packets into that existing connection and do something potentially interesting, or not, as the case may be. So, again, bit of pre-can, because obviously, while it's relatively quick to work, when I'm constrained within an hour, it's quite tricky. So one thing I've done in here is implemented a parser. So Canopy provides you with a simple GUI to implement sort of relatively simple binary protocols. But of course, one of the sort of major things you'll see is a sort of tag length value. And this is no different. You've got a tag, there's sort of the type values, you've got the minor type, then you've got a length, and then you need to read that data out. So the parser editor is clever enough to be able to provide you with dynamic arrays, and we'll read them in for you. And then we've got a subparser, which is actually doing the keyboard presses themselves. So if we start this up, oops, I can get rid of my old project now. Okay. So I've just got a simple Linux VM on here. So we open the console. Nothing's happening at the moment because the thing's not booting. But if I hit start, so that's our authentication, and now we're getting our sort of VNC packets coming out. So this was having to do 2 SSL man-in-the-middles. If you actually want to see how what it looks like, wherever it is, this thing, it started getting quite complicated. So that's why I implemented a mechanism just to do states, and that's the equivalent state as that previous graph I've just shown you, but subtly easier to read. So if we actually try and press some keys, we should now see input coming through. And there's our keyboard events. And so when we've parsed packets, what we actually now get is, instead of that binary data which we had before, we've actually now got some sort of tree. And this is also reflected in the way in which the nodes can select parts of packets to look at and manipulate. So each node implements sort of an XPath expression which you can use to exactly specify which part of that packet you want to parse. It also uses it in the filters. So, for example, if you, say, had a HTTP parser, you could say only select, only log packets which have the method of get or method of post. And you can just use that by /method, depending on how you've parsed it. But this is our keyboard. So it's all very well and good. I'll just stop that quickly. But one of the strengths of having a GUI is once you've captured traffic, you can potentially replay that. So I have prearranged some packets, which look a bit like that. Again, they're all parsed packets. But when it reaches the TCP layer, it gets reserialized back as binary data. And it's clever enough to know that in isolation of anything else. So I could take one of those packets and convert it back to binary, even though the connection isn't running or the socket server isn't up and running. So if I now just try this again, open console. Oops. Wait for it to slowly boot. So we've got our DSL. So if we go to our injector tab, we can specify we want the 902 connection, and then we specify a node, basically. So we want VNC out, inject, and hopefully you should see so. And yeah, you can just copy and paste packets around. You can just move them out from one place to another. And because they know how to sort of put themselves back together again, it doesn't really matter. And you can inject them into any part of those connected graphs and add extra traffic while the connection is running. So we'll go back to the NFC protocol. And it is a simple file transfer protocol. It is unencrypted by default, and it allows file upload, file download, all that sort of good stuff. So because there's a sort of bit of complexity in parsing this, it seemed a reasonable place to go looking for something to fuzz. For example, if you could, because it's unencrypted, there's a potential for sending packets at the side of the traffic. So even though NFC is technically authenticated, if you're actually on the local network and able to man in the middle of the traffic, you could still actually manipulate the NFC protocol itself and potentially do bad things to the system. So this is where the idea of trying to get away with no code wherever possible starts to break down. So basically the requirement of implementing this protocol is going to be something which I actually have to write some code for. Fortunately, I've already done it. And even now, the actual code itself is not exactly massive. So we've got a single Python script, and the Python script itself is not actually doing any fuzzing. So where perhaps you would expect you'd have to have written, you'd maybe bring in Sully or something like that, try and do some fuzzing. No, this is entirely just to support the functionality of the protocol, to actually implement things like sharing the session state between the HTTPS traffic, which is doing the authentication, and the NFC connection, which is then doing the implementation. And again, it's just using arbitrary clients. And I've picked out some of the basic packets. So again, the way in which it's designed, you can put in packets from a log, and these are sort of then used as your templates for your fuzz cases. The HTTPS connection now gets a bit more complicated. So I require two clients, basically. I need a client which is doing the authentication repeatedly, so that it will actually allow me to connect to the NFC service itself. And this is then storing away the session token, which the other client can then access. That's why it's a bit complicated. And so our other graphs are basically pretty much exactly the same as they were before, because our NFC is going to be doing the actual work. But the only real difference is I've now added this byte fuzzer. So when the NFC protocol kicks off, the NFC traffic will effectively traverse that route to get to the endpoint. And in the middle, we'll do some arbitrary brute force byte fuzzing. Very simple stuff. But again, this is implemented as part of the library. So you can just go to the library, and pick a fuzzer from that list if you don't want to write your own. Nothing wrong with writing your own if you need to do something very specific. But there's a reasonable amount in there. There's also it's worth pointing out, there is some parsers, so ASN1, kind of useful if you're trying and break, say, certificate validation, that sort of stuff, because you can manipulate the ASN1 byte stream. There's also DNS parsers, and HTTP. So I've said that, this wasn't really designed for text protocols, but the number of times I've come across a bespoke binary protocol, which is effectively using HTTP as a transport mechanism, it seemed to make sense to have some sort of mechanism to parse those requests and responses. So I now need to connect to debugger, because obviously we want to see if it actually crashes. This is probably the hairiest demo of the lot. It usually works just after a period of time. Hopefully that will be visible. So, the actual, even though it doesn't actually run Linux on the ESXi server, it has enough similarity with CentOS and Red Hat Enterprise Linux that you can actually just take a copy of GDB from there and run it. So we'll stop the service, which is handling the NFC, and we'll... Right. So, step one, we need to kick off our HTTP client. Right, so we're getting 200s. That's a good sign. And we now need to kick off our NFC client. And so this has an implementation of a server which will take those packets and send them along depending on what packet I get back. So there's sort of a give and take. If I see this packet coming back, send that packet, so on and so forth. And this is just represented in here. So for example, the first packet I sent is the init packets, which is just the initial connection. We then want to send download packets so we can download a file, and then a finished packet just to complete the stuff. And that ties in with the packets which are in the fuzz packet log. And it basically ties into this tag name, which is so init, download, finish. So if I now kick this off, okay, it's going through, and now we wait. Because it is doing it randomly, so in theory, it should crash at some point. There we go. So, that's our, hopefully this should still restart. So that's pretty much it in terms of the demos. So obviously I cheated a bit for time reasons, but because drawing all those lines gets very tedious and slightly error prone if you don't draw the right line in and you look bemused, and it's never good. So obviously whatever packet it was down here somewhere, but I probably shouldn't show you that. Because obviously we did find stuff. So this was sort of, we ran an internal sort of bug hunt against ESXi using Canopy. And so we had things like heap memory exhaustion panics, which is fairly typical for binary protocols. You send it a length field, it allocates that length, trusting you implicitly. And obviously then it runs out of memory. Plenty of unhandled exceptions, null pointer dereferences, use after 3 as well. Use after 3 was exploitable. And this is, as I say, the NFC protocol. So this is in plain text. This theoretically would be exploitable if you were able to man in the middle of that connection. And VMware, we've told VMware all about these, and they are fixing them. I don't believe they're currently fixed, but hopefully I didn't show anything too sensitive. So I just have to thank Alex Chapman, because he was the one that actually did most of the work. I just write the tools. I don't generally do the breaking in this particular regard. So thanks to Alex. Some references. So it's worth pointing out the version I showed is the version which should come out beginning of January. It's freely downloadable off Context's website. Unfortunately, I just ran out of time in order to actually finish it off before I came to CCC, which is a bit of a shame. So, questions?
Thanks, James.
No problem.
Thanks, James. So now it's time for questions. So if you have a question, please head to that microphone, that one, or the one on the far side of the room. I'm going to ask the first question. So you had to put the keys in, right? Like the keys aren't brute forceable. Like you were just getting the keys that were normally used in that
the SSL
interaction. Right, the SSL keys.
It was the ESXi actually just it gives you a prompt if the key is not signed by a CA. So it will just say, do you want to trust this key? And by default, ESXi actually is installed with its own self-signed cert. So an administrator probably would actually see it appear and go, oh, okay, yes, ignore. But the reason I used the existing cert was just because the protocol actually passes along information about the SSL certificate it's using. And it just requires a few extra steps to manipulate. It's nothing big, but you've got to kind of go, right, I've seen that thumbprint, replace it with my dodgy certificate. Otherwise, the client just randomly crashes.
Okay, so basically one time. One mistake on the administrator's part, and the whole thing falls apart.
Yeah.
That looks like a really useful fuzzing tool.
Thank you.
Any questions from IRC? All right. Thanks, James.
Thank you.